going to be doing derivation, preparing for your exams, which it's very crucial for you to know most, or should I say all of your derivations. Okay, we're going to look at derivation of speed of a wave on a string. Okay, this is the formula that we're trying to make up. Whatever we do, this is our goal. So if you are doing a derivation, first of all, you should have an idea of what are the expected results. So this is our expected result. We're expecting to get this. Okay, let me just get it started. Okay, so let me say you have a pulse. Why is it not straight? You have this pulse. You have this pulse moving. So we start our thing here, and we're just going to zoom in at some very small piece of the rope. So if I do that, I'll see something like this. I'm not an artist, so I'm zooming in. I'm zooming in here, showing you how it came about. Okay, so I'm cutting my thing just in between and giving this angle a name theta, and giving this one theta again. Okay, so we also know that to get our arc length, it's always equal to r theta. But from here we notice that the theta itself is made of two thetas. So our arc length, let me just put this, is going to be 2r theta. Okay, that's a very good success. So if we're looking at a small point mass, should I say, of the rope, that rope is moving. Maybe if the particle is moving like this, if you're standing here, this particle is like it's moving like this. That implies that some small particle, let me call it dm, is undergoing circular motion. Okay, so we can use that fact to help us achieve our derivation. Okay, it's undergoing circular motion. So for it to have circular motion, there should be a force let me just call it a center seeking force. So there should be a force that is pulling this thing inward the center. Okay, so then we are going to try to get that force. If you notice here, there is a tension on the rope going like this, and there is a tension on the rope. So we also assume that the tension is the same. Tension. So if I try to take this tension and draw them in a head to tail, I'll have this tension looking like this, and I'll have that one looking like this, and there will be a force that is pulling this thing into the center. Okay, and that is the force that is responsible for circular, should I say radial acceleration? Yeah, radial acceleration. So this is tension, this tension, and this tension are the same, by the way. So let me just erase this for keeping my work clean. Okay, tension, but for exam, make sure you don't erase anything. And then if I cut here, I'll have theta and theta. So remember, our goal is to get our radial force that is causing this circular motion. Okay, so we can get here we'll have, if we want to get this side, we'll have t sine theta, because it's the opposite. And if you notice very well, I was looking only at this triangle here. Okay, so if I have to look at the bottom triangle, the same thing, it's going to be t sine theta. So all this plus this is going to give me my 2 sine theta, of which is the force that is pulling this thing into the center. Okay, now we know that we can use our F net is equals to ma, of which is our Newton second, right? And this is centripetal. Okay, we know the F net. This is the force that is pulling everything in, so it's going to be T sine theta is equal to m, and for A we know a formula, it's v squared all over r. Okay, that is going to give us our centripetal acceleration, v squared all over r. Why we really bring this up? I'm bringing this because remember our attention or our interest is on v. We want to find the speed of the wave in this of waves in the string. Okay, sure. So what else do we know from here? We know that if we're looking at very small, you also need to write this for very small thetas. Sine theta can be approximated to be theta. You can take your calculator and try to put it in. These are very close if the theta is very small. So with that, we can just cut this and put theta here. That good. We also know this this mu, of which is it's a matter of the ratio of how much mass in the rope per length. Okay, that was very good. And the length of the rope, we're looking at this arc that we are interested in, so that is going to be our length, and we have that length here waiting for us, right? So it's going to be 2r theta. I'm not making it up, you just sit there. So from here on the length, I have the mass here, I will have 2r theta. Okay, this is our coefficient. Okay, remember we have mass here, so we try to solve for mass. Mass is going to equal to 2r theta mu. Okay, I'm just bad when it comes to writing these Greek letters. Okay, that is supposed to be mu. Okay, so now we have a formula for mass, so we can just come here and plug it in. We will have 2 tension theta is equal to, I prefer black, 2 tan theta is going to equal to, for mass we'll have 2 r theta mu v squared all over r. We just substituted m there, we have m here. And from here we look at the common things. We can cut down 2, it's there, it's here. We have r here, we have theta here and here. Okay, let me just write exactly what we remain with. We remain with t is equals to v squared, there is mu here remaining, and then from here we can solve for v. Because it's our interest. If I solve for v, I will have v, and I will have divided this t by this mu. It's going to be t mu, and then because of that square I will have a root. And if you look very carefully, it's exactly what we wanted to derive. So for an exam, this normally goes for 7 to 8 marks. Let me just call it 7 marks in for derivation of speed of wave in the string. So you have it. So if you find it informative, don't forget to comment, subscribe, and share the video with your classmate. Thank you.